All right. So this is 3.4, build quadratic models from verbal descriptions. Our learning objectives are to build quadratic models from verbal descriptions, thank goodness, because that's what the section is titled, and to build quadratic models from data. I thought it was important. The fact that the graph of a quadratic function has a maximum or minimum value enables us to answer questions involving optimization. And that's what I want you guys to write in your notes, is the definition of optimization. That is, finding the maximum or minimum values in models. In economics, revenue R in dollars is defined as the amount of money received from the sale of an item. Right? Revenue is the money you receive. And is equal to the unit selling price P in dollars of the item times the number of items of the unit sold. So say your family business is in dentistry and you want folks to buy an electric toothbrush so that they have better hygiene in the world. It's your gift to humanity. So your revenue is going to be how many electric toothbrushes you sell times how much you sell them for. Does that make sense? X is the number of units sold and P is the price. So what I want you to write down, I will highlight. Let's go gray. So revenue R, X units sold, P is the price in dollars, and R equals X times P. Those four things I want you to write down. And this is how you guys will take notes from your text. So obviously I'm not going to write down a whole giant paragraph when you guys are looking at your textbook. But pull the important things. If we pull an equation, like we're going to pull this revenue equation, kind of important. Please make sure you define your variables. What does big R mean? Oh yeah, it means revenue. What does P mean? It means price, and X is unit. So anytime you write down a formula, identify each of the variables when you're taking math notes. The law of demand states that P and X are related. As one increases, the other decreases. The equation that relates P and X is called the demand equation. Let's highlight this too. The equation that relates P and X is called the demand equation. When the demand equation is linear, the revenue model is a quadratic function. Because I take that demand equation, P, and it's got some X in it, and I put it multiply it by X, and I get a quadratic, because X times X is X squared. When the demand equation is linear, the revenue model is a quadratic. Okay, so here's our first example. At Hog-On Marketing Department, Texas Instruments, has found that when certain calculators are sold at a price of P dollars per unit, the number of X calculators sold is given by the demand equation. So here's what I want you to write down. Demand equation, X equals 21,000 minus 150P. Price is P dollars per unit. X is the number of calculators sold. So remember, when you write down an equation, make sure you include what the variables all mean. X is the number of calculators sold. P is the price of dollars per unit. This is our demand equation. It's how the price and the amount sold are related.
Do we use 21,000 every time, or will they give us like a different number every time?
Yeah, for each problem, the demand equation is.
Do they always give you the like, first part of it?
Yes. Okay, so A, find a model that expresses the revenue as a function of the price P. And if you look at what we wrote before, revenue is equal to X times P. So if we know that X is equal to 21,000 minus 150P, then my revenue function is going to be 21,000 minus 150P times P. So I substituted X for X in the revenue. I'm going to distribute the P. And all of a sudden we have a quadratic function. All right, so we need to figure out what is the domain of our R function. Domain of R. So we can look at what minimum value can I input for the price. What's the smallest price I can possibly input into this function? Smallest price. Very small, yes. 0. Can I make it any less than free? No. So we want to go from 0 and I don't know if we're going to be less than or equal to. So what is the biggest price we could possibly put in for our domain? Give you guys a second to think about it. Okay, so if we take a look at our revenue function, a graph of our revenue function, we see that in order to keep our revenue positive, our domain has to be between 0 and 140. And you can attain that by setting your X function, the number of calculators, equal to 0, because you're not going to produce any less than 0 calculators. You can't produce negative calculators. So P has to be in between 0 and 140. And that matches the graph, and that matches. All right, so we need to find the unit price that we should use to maximize revenue. This is where economists come in and why having a math degree is really valuable to business. If we want to maximize revenue, does this little guy look familiar? This is how we find the vertex of our function. So we know we are a downward parabola, and we know that if we find the maximum or the vertex of that it will also maximize revenue. So we're going to take our function. This guy is our A. This guy is our B. And we're going to plug it right on in to find our maximum. We're going to find the p-value that will maximize our revenue. Okay, so B is 21,000. 2 times A is negative 150. Good, because negative and a negative give you a positive. 21,000 divided by 150, I know, is 140. And 140 divided by 2 is 70. So P is 70. And let's go ahead and put the dollar sign on it so we can relate it back to what we really are doing. We're going to set a price of $70. And we're all wishing that we paid $70 for our calculator, knowing we paid over $100 for it. if this price is charged, what is the maximum revenue? So let's go ahead, take our P of 70, plug it into our revenue function, and just like on a good cooking show, I will magically get it out of the oven. All right, so my calculator spit me out $735,000. Let me double check my zeros. And then if we look at the graph that went with this, right at the top, 70 is the number of units, and 735,000 is my maximum revenue. All right, so E says how many units are sold at this price? So let's go back to our X. X is equal to 21,000 minus 150p. But in this case, our P is 70. So I'm going to calculate this out. 21,000 minus 150 times 70 equals, I get 10,500. And let's go ahead and label that as calculators. And thankfully we get to also include the graph so we can verify everything that we So go ahead and make sure you sketch this graph. Price is on the x-axis and revenue is on the y-axis. As you guys are sketching this graph, we're going to look at what price should Texas Instruments charge to collect at least $675,000 in revenue. Okay, so this is a spoiler alert. We're going to do the math that backs this up. But if you have the line y equals 675,000 on your, put it on your graph, and you look at where your function equals 675,000, that's at 50 and at 90, then you can see, okay, to make at least $675,000 in revenue, my pricing has to be between 50 and 90. But we're going to go back and do the math on this. And we're going to set our function equal to 675,000. There's that graph that goes with it. You can add this to your original graph if you would like, instead of drawing two graphs. But you look, can I divide? Let's make this into a pure quadratic. So I'm going to move everything over to this side. And it's not going to hurt us to see solving. Equals 0. Okay, so now I have a nice little quadratic. I can use that quadratic formula, or I'm pretty sure I can divide all this out by 150. Okay, so when you divide by 150, you get p squared minus 140p plus 4,500 equals 0. And then now I'm going to factor this. Now the funny part is, I already know the spoiler alert. I know what two numbers multiply to give me 4,500 and add to give me negative 140. What two numbers?
90 and 50.
90 and 50. So I did know, so it's P minus 50, P minus 90. And this is the math that backs up these points here. So I know that P is equal to 50 and 90. So the answer to this is, what revenue price should Texas Instruments charge to collect at least $675,000 in revenue? They have to charge between $50 and $90. All right, so that is a good example of a revenue problem. Let's look at maximizing area enclosed by a fence. A farmer has 2,000 yards of fence to enclose a rectangular field. What are the dimensions of the rectangle that encloses the most area? So whenever you are able to draw a picture, you want to draw the picture. So we have a rectangular field, so go ahead and draw a rectangle field. We're using X for the length and W for the width of our rectangle. So we're going to use area of a rectangle. That's one of the equations we're going to use. But what other equation do we need to employ? Because like with the revenue, we had an equation that related X and P, and then the revenue equation, we substituted in one of the values, so we just had a revenue statement with only a P. What other equation are we going to use here? We have the area of a rectangle and what? All right, so the other equation that we're going to use comes from this little piece of information here. When we have a fence, we're not going to lay the fence down to cover our crops. We are going to line our little rectangular area with our fence. And when we line something or we go along the outside of a shape, that's called perimeter. The perimeter of a rectangle is 2 times the width plus 2 times the length. That's perimeter all day, every day. So now we have 2 functions. And we know that perimeter is going to be equal to 2,000. So I'm going to go ahead and solve this for, let's solve it for W. So I'm going to subtract 2x from all sides. And I'm going to divide everything by 2. So I get W is equal to 1,000 minus X. All right, so we're going to take this area formula and instead of W, we're going to have 1,000 minus X. And then we're going to distribute. So we get a nice, we get 1,000 X minus X squared, and we can rewrite that as negative X squared plus 1,000 X. So when we find the max formula, is it tidy? So we're going to find a maximum value, and it's going to occur at our vertex. So we're going to plug in B and A. This is B. This is A. B. So we're going to plug in negative B divided by 2A. I know what negative 1,000 divided by negative 2 is going to be. It's totally going to be 500. So if X is equal to 500,
Do we go back and put that into parameter to find what W is?
we just put it right. We don't even have to go all the way back to perimeter. All we have to do is go to our W equals 1,000 minus X to find out what W is.
Which is also 500.
Mm-hmm.
Wouldn't this be a square?
It will be a square. The maximum area for our rectangular field is going to be a square. X is 500. W is 500. And let's put yards. So we know at the end of the day what we're talking about. All right, so as somebody who studied engineering, I love projectile motion. It's just throwing things and tracking its movements is exciting. So analyzing the motion of a projectile is something we do a lot. It's got a nice parabolic arc, and we find the maximum height of our missile or whatever. Thanks, North Korea. A projectile is fired from a cliff 500 feet above the water at an inclination of 45 degrees to the horizontal, with a muzzle velocity of 4,000 feet per second. 400 feet per second. In physics, it is established, In physics, it is established that the height of a projectile above the water can be modeled by h of x equals negative 32x squared over 400 squared plus x plus 500. So you guys can see in this equation how each of the pieces of information are linked. Plus 500 is what you are above the water. 400 feet per second is your speed. Negative 32 is actually the accounting for gravity, because gravity is pulling you down to the earth. So that's why projectile motion always comes back down, because it's always a negative parabola, is gravity. Thanks, gravity. All right, so make sure you can relate, because if you get a problem like this with different numbers, be able to put in the different numbers and calculate. Where x is the horizontal distance of the projectile from the base of the cliff. All right, so it looks a little something on wheels, like this little guy down here. We are going to find the maximum height of the projectile. And we know the equation to find the maximum height. Just when you thought you could forget this little vertex formula, we are going to use the heck out of it. So in our equation here, our A value is negative 32 divided by 2, 3, 4. B is 1. So I'm going to go ahead and simplify that. So our A simplifies down to negative 1 over 5,000. So let's go ahead and put that in here. B is 1, so we get negative 1 over 2 times 1 over 5,000. Because I'm a superstar mathlete, I can easily calculate that this guy, negative 1 over 2,500, and then dividing by a fraction means I multiply by the reciprocal. So this was a negative, so this is a positive. So that it is actually at 2,500 from the base of the cliff. I was looking to see if it's in feet, but my graph doesn't tell me, and I have to come back up here. Yeah, feet. Okay. So at 2,500 feet from the base, I achieved our maximum height. For A, we have to plug this in to find the maximum height. So I have to go back to my equation and plug in 2,500 to find my height, which will answer the question. Okay. So we're going to go ahead and plug that back in, so it's still on A. So I have to take my original function, and that's negative 1 over 5,000 times 2,500 squared plus 2,500 plus 500. Go ahead and do this calculation. All right, when I do my calculator chugging, I get 4,250 feet high. And now we, of course, go back to our equation and see if it makes sense. I'm looking at the graph, and I'm seeing that the graph is not at 4,000. That apex is not at 4,250. So recheck the numbers. All right, so in my calculating device, I did not put a negative in for my A value here. So when you put a negative in, you get 1,750 feet high. And that more closely matches what our graph is telling us. All right, so for part B, how far from the base of the cliff will the projectile strike the water? We talked about discriminants yesterday. The reason we do a discriminant is so we know how many zeros we're hunting for. So the discriminant is what's underneath the square root in our quadratic function. So for this situation, b squared minus 4ac, b is 1, a is negative 1 over 5,000, and c is 500. You chug those numbers together, my discriminant is 1.4. When your discriminant is greater than 0, that means there's 2 solutions. Equal to 0, it's 1 solution. Less than 0, no solutions, which is why discriminant is helpful. All right, it's also helpful because when I go to actually solve the quadratic, because I'm looking at my function, it's I'm not going to be able to factor that guy out, unfortunately. So what I'm going to do is I'm going to use the quadratic formula, negative b plus or minus square root b squared minus 4ac, which we've already calculated, divided by 2a. So I already know that b squared minus 4ac is 1.4. We have done the mathematical calculations on that. So now we just have to go negative 1 plus or minus square root of 1.4 divided by 2 times negative 1 over 5 grand. Okay, so we're going to calculate calculate this out, we are going to discard the negative answer and we're going to keep the positive answer. So go ahead and take a moment and see if you guys can calculate this out on your calculator. So in your calculator, you're going to calculate both of these answers, but the answer that is going to be viable for this equation is going to be the one where we go -1 minus the square root of 1.4 divided by 2 times -1/5,000. When we put that into our calculator, we get 5,458 feet from the base. The Golden Gate Bridge happens to be shaped like a freaking parabola. Lucky for us. Okay, so the Golden Gate Bridge is a suspension bridge. It spans the entrance to San Francisco Bay. It is 746-foot tall towers. If you look, that is this height right here. And they are 4,200 feet apart from tower to tower. The bridge is suspended from 2 huge cables more than 3 feet in diameter. Those are big old fatty cables. By the way, you don't have to write any of that down. If you just draw the picture, all of our information is in this one diagram. The cables are parabolic in shape and touch the road surface at the center of the bridge. We're going to find the height of the cable above the road at a distance of 1,000 feet from the center. So go ahead and take a moment and draw this nice little parabola on your paper. All right, so for the Golden Gate, yesterday we did the learning objective, finding the equation of a quadratic using the vertex and a point on our function. And for the Golden Gate Bridge, we have our vertex is at 0, 0, and our point is 2,100 and 526. So let me click. So we are just missing the a in our function y equals ax squared. Because if we started with our our generic equation of and we plug in 0, 0 for our h and k. We just get a equals x squared. So truly, all we're going to do is plug in 2,100 for x and 526 for y and find out what the a is in our equation. So this is going to be my x and this is going to be my y, and we're going to use that to solve for a. 526, 2,100. So A is equal to 526 divided by 2,100 squared. So let's go ahead and calculate that on our calculator. 26 divided by 2,100 squared. Get a tiny, tiny number. Let's go. So let me go 2,100 squared. I'll simplify it. So 526 divided by 4, 4, 1, 0, 0, 0, 0. And 526 is even, so I know at least I can divide it by 2. This is 263. And 4, 4, 1, 0, 0, 0, 0 divided by 2 is 2, 2, 0, 5, 0, 0, 0. So our equation for our parabola is y equals 263 over 2205, 0 x squared. That's it. If you center your parabola, so your vertex is at 0, 0, it'll make your calculations a lot easier. Okay. This is actually the easy part, building a quadratic model from data. So if I have, and you guys can actually reference your book for this data, draw a scatter diagram of the data treating age as the independent variable. Boop. So when you look at your data, does this data look pretty quadratic? Yeah, looks pretty quadratic. We're going to use a graphing utility, and I'm actually going to use an online calculating site to find the quadratic function of best fit that models the relationship between age and percent of the population. On your graphing utility, you're going to use, instead of lin-reg, you're going to use quad-reg. So it's a quadratic regression. So it's the quadratic line of best fit on your calculator. So the same thing, plug in your data and then quadratic reg, and I think it's in the same list that you found linear regression. Or if you get completely lost, go to your catalog, which is second and 0, and you can scroll or press the Q button, and it'll take you to the Q's, and it's right there. Let me finish this recording. All right, so let's finish this off. So if we go input our numbers into X and Y and calculate it out, we get that our constant is negative 26. Our B value is a 1.47, and our coefficient for X squared is a negative 0.0136. You're going to then take that equation, so write this equation down and answer the questions. Which percentage of the population divorced the greatest? So finding the maximum. And use the model found in Part B to approximate the highest percentage of the population that is divorced. And then draw the quadratic function. And that's it for data and today's lesson.